Hey guys, today we're going to be talking about a really important concept in chemistry, and that is how to assign oxidation numbers to atoms and elements within compounds, but also when they're by themselves. Assigning oxidation numbers is really important in chemistry because oxidation numbers can sometimes change over the course of a chemical reaction. We really need to be able to know how to track that because that's critical understanding for in terms of when electrons move. And so electrons can be transferred from one atom to another over the course of a chemical reaction, and in that we call that oxidation and reduction. So we're going to explore both of those things today, how to assign oxidation numbers and also how to recognize oxidation and reduction over the course of a chemical reaction. So let's go ahead and get started. Let's first discuss what is an oxidation number. An oxidation number is essentially the number of electrons lost or gained by an atom within a compound or when it's by itself as an ion. One of the most important aspects of oxidation numbers is that they are not charged. And you can't refer to it as charge because charge suggests that electrons have been lost or gained completely, whereas oxidation numbers, that's not actually the case. In compounds, oxidation numbers are not truly lost or gained, even in the solid ionic forms. So there's a little bit of a difference there between oxidation numbers and charge. And you want to be very clear about when you're talking about oxidation numbers, you are talking about oxidation numbers. When you're talking about charge, you're talking about charge. So let's keep those clear and separate. So let's start with the first rule of oxidation numbers. And that is that the total sum of the oxidation numbers in a compound or an ion must add up to the overall charge of that compound or ion. So many compounds are neutral, which means that the sum of oxidation numbers must add up to 0. But in some cases, we're dealing with polyatomic ions. For instance, H3O+, this is the hydronium ion, and in the hydronium ion, we have a +1 charge. This means that the sum of oxidation numbers of all atoms within the hydronium ion must add up to +1. With hydroxide, OH-, this means that the sum of the oxidation numbers of all the atoms within the compound must add up to -1. Water, because it's neutral, that means that the sum of oxidation numbers must add up to 0 because this water molecule is a neutral molecule. Now that we know that the sum of all oxidation numbers of atoms within a compound must add up to the charge of the compound, let's look at some special cases. Diatomic elements are going to be 7 elements which end up as, anytime they're in nature, for instance, anytime oxygen is in nature, it's not just O, it's O2. And so diatomic elements always pair off in nature spontaneously, which means that if you're going to look at oxygen in nature as a gas, it's always O2, and nitrogen is always N2, and chlorine is always Cl2. These are our diatomics. There are 7 of them. The way I remember our 7 diatomics is with Hunkel-Briff, HON-Cl-Br-I-F. H for hydrogen, O for oxygen, N for nitrogen, Cl for chlorine, Br for bromine, I for iodine, and F for fluorine. These are our 7 diatomic elements. Now, because they are diatomic elements, we consider them to be in their elemental form when they are in their diatomic form. For instance, H2 is elemental hydrogen. O2 is elemental oxygen. These are really important rules because that's a key factor for when we get into not just here in oxidation number assigning, but also thermochemistry. So it's important to remember our 7 diatomics like the back of your hand. So for the diatomics, their oxidation numbers are set at 0. And that's the case for any atom, including our 7 diatomics, is going to have an oxidation number of 0. This means that if you have sodium, Na, in its elemental form, so solid sodium, it's going to have an oxidation number of 0. Solid aluminum, oxidation number of 0. So what this means is that we need to look at the whole compound first before we start trying to assign oxidation states. So let's do some examples where we do look at whole compounds and then assign oxidation states based on these rules that I've discussed. Which again, just to remind you, the most important rules are that number 1, the sum of oxidation numbers adds up to the total charge in the compound. 2, that when you're dealing with the elemental form of any atom, the oxidation number is 0. And 3, there are some atoms that are more electronegative than others, and some atoms that are less electronegative than others. And because of that, we have to assess the relative electronegativities of atoms in a compound to be able to correctly assign oxidation states. In addition to those, here are some common oxidation state rules that you're going to want to know. Take a minute, pause the video, and go ahead and write these down so that you'll have them for future reference. So let's do some examples so we figure out how to assign oxidation numbers to different types of atoms in different scenarios. So the first one we're going to look at is an atom by itself. This is an aluminum atom. Now, because it's by itself, we know that it's in its elemental form. That means its oxidation number is going to be 0. Chlorine is one of our 7 diatomics. Remember, Hunkel Briff. So chlorine, because it's also in its elemental form, would have an oxidation number of 0. However, in this case, chlorine is in its ionic form. Now, remember, the sum of oxidation numbers is going to add to the total charge. Well, the charge of this chlorine ion is -1. Therefore, the oxidation number of this chlorine ion is also -1. Now we get to a compound. Water, if you look at the overall compound, has a total charge of 0. That means the sum of oxidation numbers needs to add to 0. Oxygen is more electronegative than hydrogen. That means the oxygen is going to have the negative oxidation state, whereas hydrogen will have the positive. So oxygen in this case is going to be -2, and each hydrogen would be +1. Because there are 2 of them, the total oxidation number contributed by hydrogen atoms is +2, which means that adding it to -2 would give us a sum of oxidation numbers of 0, which is the charge of the compound. This perchlorate ion, ClO4, is going to have an oxygen and a chlorine atom in it. It also has an overall charge. So the first thing we need to recognize is that the sum of oxidation states is going to add to -1. The second thing we need to do is we need to look and see which is the more electronegative atom of the 2. In this case, it's oxygen. Oxygen is going to have a -2 oxidation state, which means each atom is going to have a -2 oxidation state because it's the most electronegative atom. Therefore, chlorine is not going to be the most electronegative, so it'll actually have a positive oxidation state in this situation. Oxygen, because each one is -2, but there are 4 of them, we know that the oxidation number of chlorine must add to the total oxidation number contributed by the oxygen atoms, which is -2 times 4, and that must add to -1. Therefore, if we solve for x, we know that the oxidation number of this chlorine atom must be +7. So this is a situation where we had to, number 1, recognize the charge of the polyatomic ion. Secondly, identify the most and least electronegative atom within the polyatomic ion. Third, do some algebra to determine what is the charge of the oxidation number of the least electronegative atom, in this case the chlorine. So let's do that again for lead nitrate. Now, there's a trick we can use here with nitrate, and that's we know nitrate has a total charge of -1 because it's one of our very common polyatomic ions. Because there are 2 of them, we know the lead must be +2. And within each nitrate, NO3-, each oxygen, because it's the most electronegative atom, is going to be -2. Therefore, the nitrogen must add to those oxygen atoms' oxidation numbers to give us a total charge of -1. So what ends up happening here is we say, okay, if we've got NO3-, each oxygen is going to be -2, and there are 3 of them. So adding this oxidation number of nitrogen to the total oxidation numbers contributed by the oxygen must add to our total oxidation state of -1, the charge of the polyatomic ion. That means each nitrogen in this compound must have an oxidation state of +5. So this is a tricky type of problem. But again, if you break it down, you look at the polyatomic ions separately, you can easily figure out the oxidation state of that metal, just like we did with ionic compounds when we were doing nomenclature. The second thing we can do is look at the independent ion itself. So looking at the nitrate by itself to figure out the oxidation state of the least electronegative atom, in this case the nitrogen. Now let's take the next step. The next step of this is going to be assigning oxidation numbers to elements and compounds within chemical reactions. We're going to do this the same way we did it before, which is we look at an individual compound and we assign oxidation numbers to every atom within that compound. For example, hydrogen peroxide. Now, the hydrogen in hydrogen peroxide is going to be the least electronegative atom, and the oxygen is going to be the most electronegative. Remember that peroxides are one of our exceptions for oxygen. Normally, oxygen's -2, but in peroxides, it's actually going to be -1. The hydrogen, because it has only one electron to give, is going to be +1 in this situation. So we've got +1 for the hydrogen and a -1 for the oxygen. You add them together, and the overall sum of oxidation numbers, +2 and -2, add to 0, which is the overall charge of our compound, hydrogen peroxide. On our product side, we have water. Now, we already assigned the oxidation number for water in the past, but let me just remind you, oxygen is going to be -2. Hydrogen, each one's going to be +1. And in elemental oxygen, just like any other elemental compound, we end up with an oxidation number of 0. Remember, all of our elemental compounds are the diatomics, Hunkelbrief. Now, if you look at this, we've accurately assigned oxidation numbers to every atom within the compounds. Hydrogen is +1 here, and it's +1 here. But you'll notice that oxygen in our reactant is -1, but in our product, within water, it's -2, and within elemental oxygen, it's 0. So its oxidation number actually changed. That's a really important observation to make, because what that tells us is that we have just undergone what is called a reduction-oxidation reaction. So let's talk about reduction oxidation very quickly. We're going to talk about more of this later in the unit, but I want to introduce you to the concept now. The first thing you need to understand is that reduction is the gain of electrons. Meanwhile, oxidation is the loss of electrons. Now, really handy mnemonic you can use for this is oil rig. Oxidation is loss, reduction is gain. Another one that's really common is Leo says Ger. Loss of electrons is oxidation, gain of electrons is reduction. But my personal favorite is Olé. Oxidation is loss of electrons. Now, the rule with Olé is you actually have to do the hand motion to it. So you have to go Olé. If you don't do that, then you can't use this mnemonic. You have to use one of the others. So this is your basic introduction to oxidation and reduction. Now, what that means is that the oxygen that went to the water went from -1 to -2. That means it gained 1 electron. Because each electron has a -1 charge, it must have gained 1 electron to go from its -1 oxidation state to its -2 oxidation state. It gained an electron. That means it was reduced. The oxygen that ended up in elemental oxygen went from -1 to 0. That means it had to lose 1 electron to go from -1 to 0, which meant it was oxidized. So in this situation, an oxygen atom was oxidized and an oxygen atom was reduced over the course of this chemical reaction. This is how we know it's a redox reaction. Any redox reaction, if one thing is oxidized, another thing must have been reduced. In this case, those two things happen to be atoms of the same element, but they were two different atoms, two different oxygen atoms, one which gained an electron and one which lost an electron. Now what we're going to do is we're going to do some practice problems that you're going to try. And what you're going to do is you're going to try some practice problems, and then you're going to work through them, all right, and we'll work through them together once you get answers. Now I'm going to have you do 2 practice problems where you're going to assign oxidation numbers within these chemical reactions. And once you do that, I want you to identify the element which is being oxidized and the element which is being reduced in each of the chemical reactions. So take a look at these two reactions behind me. Pause the video. When you get an answer, if you get stuck, unpause the video and we'll talk through the answers. All right, so let's see how we did. We're going to look at each compound individually, and then we'll go through and identify what is being oxidized and reduced once we get the oxidation numbers of everything. In sodium hydroxide, hydroxide is one of our polyatomic ions, has an overall charge of -1. Therefore, the sodium must have an overall oxidation state of +1. In hydroxide, the hydrogen is going to be +1, and the oxygen is going to be -2. Chlorine, because it's its elemental form, oxidation number of 0. Looking at our products, sodium chloride, sodium is going to be +1, and chlorine -1. Sodium, in this sodium hypochlorite, is going to be +1, oxygen -2, and chlorine +1. And in water, oxygen is -2, and hydrogen is +1. Now, if you look across, we can see some of the elements, their oxidation numbers changed, whilst others did not. For instance, sodium is +1 here and +1 here. No change. Therefore, it's not involved in this redox reaction. Oxygen, -2. And on both of the products, oxygen is still -2, so it did not change. Hydrogen is +1 here and +1 here. It also did not change. Chlorine, however, went from 0 to -1, and also from 0 to +1. That means the chlorine is both oxidized and reduced over the course of this chemical reaction. So the chlorine is being oxidized from Cl2 to NaCl, and it's being reduced from Cl2 to NaCl. Let's look at the next one. Permanganate ion. Permanganate has an overall charge of -1. Each oxygen is going to be -2 within it. That means the manganese must have had an oxidation state of +7. Iodine, as an ion, just has an oxidation state of -1. Hydrogen is each going to be +1. On the product side, the manganese is going to be now paired with MnO2. Oxygen's -2, manganese +4. Iodine in its elemental form here, oxidation number of 0. And water, oxidation number of oxygen is -2, hydrogen is going to be +1. So now we've assigned oxidation numbers to every atom within the compounds. Now let's take a look for oxidation or reduction going on. Manganese went from +7 to +4. This means it became less positive. Less positive means also moving more negative. In order to move towards the negative, that means it needed to gain electrons. If it gained electrons, that means it was reduced. The iodine, meanwhile, went from -1 to 0. That means that it lost 1 electron each. Therefore, it was oxidized. So there you go. So that wraps up today's video. Today we talked about how to assign oxidation numbers to atoms within compounds and also when they're just by themselves. We talked about the 7 diatomic atoms, which are really important to know and memorize for this year. And then we also did some example problems where we looked at the most and least electronegative atoms within compounds in order to correctly assign their oxidation states. I want to thank the students who wrote, filmed, and edited this video: Sam Zonderman, Jack Turgeon, and Jacob Wynn. I want to thank you guys so much for watching it, and I'll see you in the next video.